extremely photon efficient.
So
and of course, it gets better with time. Of course, there's no improvements, and so this is a very strong concept.
Yeah. So we will have some difficulties concerning about the emission of the photons. Since bacteria is a 3D, and if that the emitter, do you have some problems when you're the depth or something coming from a special place?
Not necessarily. As I said, the strength of the concept, unlike Palm Storm, is that you have a confocality, and that limits, of course, the detection volume in 3D. So I have not shown it, but I would not be surprised if this thing would work deep inside an object, because you have this discrimination. I'm not saying it's going to work and it's going to work well. I don't know at this stage, but the concept is powerful enough to give it a go. So you think about it. The strength of the concept is that you determine the position to a large extent with the structured beam, and then if you set it up confocally as we've done it, you have an additional background suppression. This is why this is going to fly. I'm 100% sure.
Okay, the question at the back, and then there.
Good afternoon, Professor Hao. I'm very excited to be here because I have traveled thousands of kilometers to here and from Guangzhou. Actually, I'm from Sun Yat-sen University, Zhongshan Daxue in Chinese. So I'm a researcher of computer science, and I have two questions for you. The first question is that, do you think it is possible to develop a single-shot storm? I mean, using only a single frame to get a perfect image, perfect clear image. Yeah, that's the first question.
You must explain to me afterwards how you do that with a single shot.
Actually, the question is that in your work of storm and step, you use thousands, even millions of frames to obtain a clear image of the details, right? My question is that, do you think it is possible to reduce the number of frames to 1 to get a clear image?
I have difficulties imagining that as long as you play on-off, because the things that they are off at time point 1 must be turned on at time point 2, and this cannot be done in a single frame, unless you separate with something else, with color or something, then it's possible. But if it's classical storm or palm, that is fundamentally based on time sequential emission, like STAT2, it's time sequential emission. So in a single shot, you cannot do a separation by on-off, unless you do the separation differently. But you tell me afterwards how you do it.
Actually, our research group has work on this topic. And the second question is that, if I have a computational method that can separate all the molecules, all the spots, all the particles at 1 frame, do you think it is possible to collaborate with our group?
I didn't get. What was the question? Can you repeat it?
Can you ask one more time, slowly?
Okay. I have to try to say it slowly. And actually, our group has work on this topic, and we are now able to get a clear image from only a single blurry image from the microscope.
Okay, I'm very curious to hear about the physical principle.
Yes, actually we have realized that in a common microscope system, and is it possible that we can collaborate on this topic?
We talk afterwards.
Yeah, you can discuss afterwards. So you're done with your second question, right?
Yeah, that's my second question.
All right.
That's all.
Good.
Thank you.
Yeah. There's a question over there.
So here. Oops. So my question here is, for the structure illumination, so in this case, to increase the signal-to-noise ratio, probably for example, for live cells, one might choose a sort of a longer wavelength in a way to avoid the autofluorescence, and therefore one can have better signal-to-noise ratio. But for the in vivo imaging, efforts probably need to make to achieve a good donor structure to sort of achieve a better resolution. What will be your thoughts regarding, for example, combining with some nonlinear photonics like two photon to create a special structural pattern for the in vivo application?
I mean,
where the
as you were saying,
scattering of the lights might sort of distort the structural illumination in a deeper tissue.
That, I mean, as you were saying, I mean, I don't know if I understood you correctly, but of course, usually the STAT beams are long wavelength beams in the near infrared. And of course, these beams are much more robust when it comes to penetration into, say, deeper tissue or something. Of course, they are also facing aberrations. Of course, there's scattering, but there's less scattering and fewer aberrations. I know people work on these. I've never worked on it. So I know there is potential for correcting aberrations. I know that a commercial system, that little box, and related systems, they can in principle, and the big box, as a matter of fact, has ways of correcting aberrations with LCD displays and things like that. And there's many ways of counteracting it. I have no personal experience with that. But that's what I would do if I were interested in going deeper down into tissues. I think when it comes to neurosciences, so STAT should not be underestimated, because in my view it's the only super-resolution method right now that can get down to the level of a synapse and lower under live system conditions like mouse conditions. And it's not only us who have a paper now, just yesterday, but there's also others. There's this man, Valentin Nagel in Bordeaux, who has published connections between neurons in tissue and even live cell hippocampal imaging with that. Because that's the only way, that is the only way to get at this scale. And so there's a lot of potential. I think, in my view, too few people have taken advantage of that. Too much is going to mainstream other type of stuff, electron microscopy and I don't know what.
I see many questions are technical. You can ask technical questions, but I also encourage I see many graduate students here. Stefan started doing creative research when he was a graduate student. He invented 4-pi microscopy. That was his first super resolution microscopy. So feel free to ask non-technical questions. You.
Hello, Professor here. Actually, I have a very simple question. As you mentioned, the MinFlex is a very great tool and has very new application or novel applications, especially in the structural biology. I'm wondering whether this technology can be used in the lab cell to study the protein folding at the current stage.
Study what? Sorry, I didn't get it.
And use this technology to study the conformational change of our protein in live cell.
To study conformational changes in protein in live cells.
Yeah.
I think that should be possible, yeah. I think this is one of the reasons why we're developing it. We're not doing it at this point. As I said, I'm not a biologist, but we get it better and better and better. And I think this is something interesting, that you really see conformational changes or molecular aggregations on a single molecule level under living cell conditions, yeah.
Mm-hmm.
Yeah.
So,
and without a generalized method such as FRET, where you get only bulk or a coarse yes and no answer and so on.
Mm-hmm. Thank you.
Sorry, another technical question. And so for mean flux, it measures the location with very small number of measurements, like 2 measurements for 1D and 4 measurements for
Correct.
2D.
Yes.
So would it be more easily to influenced by the statistical noise? And since the measurements are performed at different time points, so would the fluctuation of the fluorescence influence the localization accuracy?
I mean, the natural fluctuation of the fluorescence, I mean, the Poissonian fluctuation is there, of course. So that's taken into account. You are right in a sense that the 4 points have to be measured in quick succession, because if they're not measured in quick succession, the molecule may have moved. The fluctuation per se, which is intrinsic, is normal. This is taken care of, I mean, by considering the Poissonian statistic of the emission. But what is of course an issue is if the molecule moves within the time frame that those 4 measurements are being taken. Of course, it need not be just 4. You can also circle that thing around, or you can make another type of movement, or there are many ways of imagining that. So the 4 points are kind of, well, good for explaining things. It was made like that, but you can imagine other constellations. As long as you determine the position with the donut, you're within the framework of the concept.
Okay, thank you.
Thank you, and I have a small question. So we know if 2 molecules located nearby and they could transfer the energy from the maybe activated and inactivated molecules. So will this crosstalk be another barrier when we push the resolution limit of the super resolution microscopy?
Again, I didn't get it full. So maybe the acoustics here is not great.
Yeah, so if 2 molecules are located nearby and
Yeah.
One is activated and one is inactivated,
Yeah.
So the activated molecule may transfer the
Yeah.
energy to the
They do.
inactivated when they located in maybe.
They do.
Yeah.
They do, yeah. So this is clearly a conceptual limit of any fluorescence microscopy. It has nothing to do with the concept. So once you get to molecular distances, you will face this problem. Actually, we've seen that in our measurements. So this is why this 6 nanometers and smaller was difficult to do with the same type of molecule. Of course, you can always say, well, if it transfers the energy, so what? We hope that we measure at some point where the energy is not transferred. We have to try more often. But there could also be, say, like exciplex formation and this type of stuff. There could be even more naughty things. It's a limitation of fluorescence microscopy per se. Of course, fluorescence microscopy has the problem that it images only fluorescent molecules, nothing else, not the proteins, but the fluorescent molecules, not more than that. And these fluorescent molecules have their own life, and at some